Now we want to think about how conservation of energy works in a fluid. This is a little bit different than thinking about conservation of energy in a solid. In a solid, you pretty much have one way of expressing the energy, kinetic energy. So if you do work on a solid, it's going to speed up, it's going to increase the kinetic energy. If you do negative work to a solid, you're going to reduce the kinetic energy because it slows down. So pretty much there's just kinetic energy is the one form of energy involved here. In a liquid, we have two forms of energy. You have kinetic energy, which is related to how fast the liquid flows, but you also have pressure. We can think of pressure as a form of internal energy, and so there's a second way that the energy in a liquid can be manifested. So, more specifically, we want to convert the kinetic energy, potential energy, and work that we've been thinking about before and change it into the appropriate form for a liquid. Let's start with kinetic energy. So kinetic energy is 1/2 times the mass times velocity squared. So in a fluid, the mass is the density times the volume. So let's rewrite the kinetic energy as 1/2 times rho, the density, times the volume, times the velocity squared. And this is exactly what we had before. It's a perfectly good equation for the kinetic energy. For gravitational potential energy, we've kind of already done this. Potential energy is mgh, so the potential energy of a fluid is the density rho times volume to give us the mass, and then multiply that times g and by height. So we get the potential energy is rho times volume times g times height. Lastly, we've mentioned that pressure can be thought of as another form of energy, and the work done by pressure is equal to the pressure times the volume. If you think about it, pressure is the force divided by the area, and then the volume is the area times the displacement. So essentially, pressure times volume is the same thing as force times displacement, which is the same thing as work. So you'll notice that all of these are proportional to the volume. So if we want to find an amount of energy per unit volume, we can just divide all of these forms of energy by the volume and get pressure plus 1/2 rho velocity squared plus rho gh, and that must all be equal to some constant as long as the volume remains constant. So we can use this formula called the Bernoulli equation to see how the pressure changes in a fluid depending on the situation. So we're basically going to consider two situations using the Bernoulli's equation. One is the case where the area of the pipes are constant and we change the height. Or we can do something different where we keep the height constant and change the area of the pipes. First, let's consider the case where we change the height. The first thing to notice is that due to mass balance, when we raise the height of our pipe, the velocity can't change. We need mass balance to hold at every point in the pipe, but as long as the same amount of water is being added to the pipe, then the velocity of the flow must remain the same. What needs to change is the pressure. This means that the kinetic energy is exactly the same at the new height and at the old height. So pressure 1 plus rho gh of 1 is equal to pressure of 2 plus rho gh of 2. That means if the potential energy increases, then the height increases and the pressure decreases. If the height decreases, then that means that the pressure must increase. The other effect is when the area of the pipe changes. Here, we have a pipe whose area has decreased. Well, the potential energy is the same before and after, so we can forget about the potential energy for the moment. However, when the tube area decreases, the velocity of the fluid must increase to keep the mass balance, right? It's the same volume of liquid must enter and leave the interface. The reduced area means the velocity increases. If velocity increases, then kinetic energy increases. If kinetic energy increases, well, that means the pressure must decrease. Remember, the pipes are fixed, so we are putting no additional energy in the system. That means when the kinetic energy of a fluid increases, then the pressure decreases due to conservation of energy. So yeah, this is kind of a surprising result, I think. Probably the most famous example of Bernoulli's principle is an airplane wing. So the details of this is kind of complex, but the big concept here is that the velocity of the air on top of the wing is greater than the velocity of the air underneath the wing. That means the pressure of the slow area underneath is greater, so a force pushes the wing up and gives it lift. I tend to sort of think of it is that underneath the wing you have a pocket of air that's protected, so the velocity is lower, and on the top of the wing it's curved, so the air moves rapidly right next to the wing, lowering the pressure. But the big point is that due to differences in the wind speeds, this causes lift due to Bernoulli's principle, where the higher wind speed results in a lower pressure. You can demonstrate this to yourself if you just take a piece of paper and blow along the top of it, so just sort of parallel to the paper. It seems like it should be obvious what happens. Blowing should push the paper down. But weirdly, if you blow at the right angles, just kind of parallel to the paper, the piece of paper will actually pop up. And the reason is that the pressure above the paper becomes lower than the pressure below because the velocity of the air has increased. So that difference in pressure causes the paper to pop up for a second. Okay, you have a couple of quick conceptual problems about Bernoulli's principle, so do those and then we'll work through a more quantitative example in the next set of slides.